Hess's law. German Henry Hess states that when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. Means there are several ways for reactants to be converted to the product. The change in enthalpy for one step from reactants to become a product, and for several steps from the reactant to become the product, the change in enthalpy of both are the same. Whether one step or several steps, the change in enthalpy are the same. Hess's law allows the enthalpy change, delta H symbol for the enthalpy change, for a reaction to be calculated even when it cannot be measured directly. We know that delta H means the enthalpy of the product minus enthalpy of the reactant. So that is delta H. So we cannot measure it directly, but we can measure the change of enthalpy for a reaction. For example, here, the reactant X to becomes the product Y, the enthalpy change, delta H1. So this is one value, the enthalpy change, one value from reactant X to becomes product Y. And then the reactant X can become the product Y by becoming the product A first and then becoming the product Y. So this reactant X converted to the product A by having enthalpy change 2, delta H2, and then from here, from product A to becomes a product Y, it has enthalpy change 3, so delta H3. So here, this value, delta H1 value, is equal to the value of delta H2 plus delta H3. So that is Hess's law. The change in enthalpy is the same whether reaction takes place in one step or a series of steps. Means this delta H1 equals to delta H2 plus delta H3, and same for the reactant X to become the product Y. This reactant X becomes product B and then converted to product C first before becoming the product Y. So from here, delta H4 plus delta H5 plus delta H6 is equal to delta H1. That is Hess's law. Enthalpy change is the same. As long as this reactant X will become the product Y finally, it doesn't matter in the middle it will become B or C or A, as long as finally it will become Y. So delta H1 is equal to delta H2 plus delta H3, and then it's also equal to delta H4 plus delta H5 plus delta H6. There are two methods to calculate delta H, the enthalpy change. The first one is algebraic method, and the second method is energy cycle method. Example 1, this is the algebraic method. Determine the enthalpy change for the following reaction by using algebraic method and energy cycle diagram. So I'm going to show you the algebraic method first. Here is, we need to find the enthalpy change of the reaction from the chemical equation 2NO plus O2, and the product is 2NO2. And we need to calculate the enthalpy change of this reaction. Given enthalpy change for half N2 plus half O2, the product is NO, given the enthalpy change is plus 90.37 kilojoule per mole. So here, positive sign means this is endothermic reaction. Another equation, half N2 plus O2, you'll get NO2 as the product, and the enthalpy change is equal to positive 33.8 kilojoule per mole. This is also endothermic reaction. From these two given equations, you need to find out the delta H from the targeted equation. So this is our target equation. By using algebraic method, the target equation, write down it first, and then if you look at here, our target equation, the NO is the reactant, oxygen is the reactant, and NO2 is the product. So if you look at the equation 1 and equation 2 again, the NO, which is in our target equation, the NO is the reactant. But in this equation, our NO is the product. So you have to reverse this equation to make this NO to become the reactant. If you reverse this equation, it will be NO as the reactant, O2 and N2 as the products. If you reverse the equation, you have to reverse the sign as well. This sign will be negative, but the value will remain the same. And if you look at NO2, NO2 is the product. In the second equation, the NO2 is the product. So you don't need to reverse this equation, just write down this equation. And then we rearrange for this one. For NO, we have to rearrange, we have to reverse the equation. And note that in our target equation, we have 2 mole of NO. In the equation given, we only have 1 mole of NO. In order to become 2 mole of NO, you need to times this equation with 2. Multiply with 2. So this will become 1, this will become 1, and this will become 2. And reverse this equation because NO must be the reactant. And the value, you have to change the sign and you have to times by 2 as well. Because you times the equation by 2, times the value by 2 as well. Reverse and multiply by 2 and you will get this equation, new equation 1. So if we reverse this equation, the NO becomes a reactant, N2 and O2 becomes a product. And then we times by 2, so the NO 2 mole, the N2 initially half, now it is 1 mole, same goes for oxygen, 1 mole. And this delta H, change the sign to negative and times by 2. So 90.37 times 2, it is 180.74 kilojoule. So this is kilojoule, not kilojoule per mole anymore. Because per mole is for this NO, because this NO is 1 mole. When you multiply by 2, this NO is not 1 mole anymore. So don't write down per mole here. It is just kilojoule. That is the first equation when we reverse and multiply by 2, and it's the same as the target equation, reactant 2 mole. Next, the second equation. Second equation is half N2 plus O2, the product is NO2. Look at the product, NO2, here NO2 is the product, so you don't need to reverse this equation, but in the target equation, 2 mole of NO2, so you have to multiply this equation by 2. Multiply this equation by 2 and multiply the delta H as well. And then the new delta H will be positive 67.6 kilojoule, not per mole, because per mole for N2 1 mole per mole. Now your NO2 is 2 mole. So don't put per mole here. Delta H2 is kilojoule only. And you have to multiply by 2. This is half multiplied by 2. You will get 1 mole. And oxygen 1 mole multiplied by 2. You will get 2 mole of oxygen. Now these two are your new equation. These two are your new equation. Write down, combine your rearranged equations. These are your new rearranged equation. And then you have to make this as the target equation. So in our target equation, we have 2NO at the reactant. And then, look again, 2NO as the reactant, 1 oxygen as the reactant, 2NO2 as the product. So this 2NO as the reactant, write down back, and then oxygen in the target equation, you only need 1 mole of oxygen. But here, in your rearranged equation, at the reactant side, you have 2 mole. You only need 1 mole of oxygen. So here, 2 mole oxygen at the reactant and 1 mole oxygen at the product. You can cross or cancel out this 1 mole oxygen, cancel out 1 mole oxygen, leaving this oxygen 1 mole. And then, in your target equation, you only have NO and O2. But here, in your rearranged equations, you have N2 as the reactant. We don't need this N2 as the reactant. We need to cancel out this N2 by cancelling out N2 with the N2 of another equation at the product. So cancel out reactant N2, cancel out product N2. So we cancel out oxygen and N2. Note that this oxygen, you only cancel out 1 mole, leaving you with 1 mole. So here you get the new target equation. This is your target equation after you cancel out your combined rearranged equation. This is your target equation, and you have to calculate the delta H of this reaction. When you do this, just add whatever equation you have in here. So delta H is equal to delta H1 plus delta H2. That is your delta H reaction. You add this negative 180.74 plus positive 67.6. Your delta H reaction is equal to negative 113.14 kilojoule. Not per mole, kilojoule. So this is how you apply Hess's law using algebraic method. Next, I'm going to show you by using energy cycle method, the second method for applying Hess's law. Step 1, write down the target equation, 2NO plus O2, the product is 2NO2. We need to determine the delta H reaction. So this is equation 1 given in the question. Again, we have to reverse and multiply by 2 like I've said before, because your NO must be at the reactant. Here, NO must be at the reactant, so you have to reverse and you multiply by 2 because you need 2 more of NO. Here in the equation given, only 1 more. So when you reverse, you'll get 2 NO products and 2 NO2. Delta H1 equals negative 180.74 kilojoule. And when you've already calculated this, focus on the reactant 2NO. The products are 1 more N2 and 1 more oxygen. So here you have reactant 2NO, and draw this arrow to becomes a product, 1 more N2 plus 1 more oxygen, and delta H1 equals to negative 180.74. You have to label the delta H for your rearranged equation here. And then next, your equation 2 is this one given in the question, and here product 1 more NO2, but in the target equation 2 more NO2, so you need to multiply this equation by 2. Multiply that equation by 2, multiply for all reactants and product in there, and you also multiply the value of delta H. You will get 1 more N2 plus 2 more oxygen, the product 2 more NO2, and delta H2 equals this value times 2, plus 67.6 kilojoule. So this is the new value when this delta H multiplied by 2. And then if you look at here, the product is 2NO2. So this is the product. You need to draw the arrow from the reactant N2 and 2O2. So here, this is N2 and then plus O2. This is from what you have here, N2 plus O2. But you need now N2 plus 2O2, you'll get 2NO2. So you need to draw the arrow from here to this one. And the arrow will be delta H2 equals to positive 67.6 kilojoule. This is for the delta H2 equals positive 67.6 kilojoule is for N2 plus 2O2. The reactant must be N2 plus 2O2. So here, before O2, you just need to add 2 more of O2. Add 2 more of O2, and then your energy cycle diagram is complete. The oxygen must be written in the equation, not on the arrow. On the arrow, you only can write down the delta H, the enthalpy change. But for the reactant or the product, it must be before or after the arrow. Don't write on the arrow. And then next, you can apply the Hess's law. Delta H reaction equals to delta H1 plus delta H2. Look at here again. So delta H reaction is equal to delta H1 plus delta H2, because this is a single step. This first step and second step. So the value of a single step from this reactants to become the product is equal to the delta H of the second step and plus the first step. So these two steps, delta H equals to one step delta H. That is Hess's law. So you just sum up the H1 and H2, substitute the value, don't forget the negative sign, because this delta H1 is exothermic. If you put the negative sign, and you will get the delta H reaction equals negative 113.14 kilojoule. So this means this reaction is exothermic reaction. Next, determine the delta H naught reaction, standard enthalpy reaction from the standard enthalpy formation. So we have the standard enthalpy formation. We need to calculate the standard enthalpy reaction. For example, we have the equation A plus B as the reactants and C plus D as the products. And we need to calculate this delta H reaction. Enthalpy change for this reaction means the heat, amount of heat of the product minus the enthalpy of the reactant, that is delta H reaction. So the delta H reaction equals to this small letter c is the stoichiometry of the equation, and it times with the delta H naught formation of C plus the delta H formation of D minus the reactant delta H formation, and it must times with the stoichiometry for each. So we can conclude that delta H reaction, the standard enthalpy reaction, equals to total or sum of delta H naught formation of all products minus total or sum of delta H naught formation of all of the reactant. So total all product minus total reactant enthalpy change formation. and you will get enthalpy change reaction. The enthalpy change reaction can be calculated by using this formula if the delta H formation of all elements or atoms are given. You can only use this formula if you have the information for all delta H formation products and all delta H formation of reactants. Then you can use this formula. If not, you have to use the algebraic method or this energy cycle method. Example, nitric acid, whose worldwide annual production is about 8 billion kilogram, is used to make many products including fertilizers, dyes, and explosives. The first step in industrial production process is the oxidation of ammonia. This is the chemical equation of oxidation of ammonia, means ammonia reacts with oxygen, and the equation is balanced. And we need to calculate the delta H reaction, standard enthalpy reaction, given the standard enthalpy formation for all of the reactants and product. So here we have for NH3, we have for NO, we also have for HO2, but the oxygen is not given. Remember that oxygen is in its most stable state, O2 gas. So delta H formation for elements at its most stable state is equal to 0. So now you have the delta H formation for all reactants and products. You can use the equation of sum of delta H formation of all products minus sum of delta H formation of all reactants. Standard enthalpy change of the reaction is equal to, you have to take account the number of mole or the stoichiometry for each reactant and the product. So here 4 times the standard enthalpy change formation of NO and the standard enthalpy formation of H2 times with 6, because here is 6 mole, for here NO 4 mole, minus some standard enthalpy formation of reactant, here 4 times NH3, and then 5 times 0 is 0, so you don't need to write down this oxygen because the standard enthalpy formation of oxygen is equal to 0. So just substitute these 3 values into this equation and you will get the standard enthalpy reaction equals to negative 906.0 kilojoule. So this is the equation that you use when you have all the information of standard enthalpy formation for all reactants and all products. Here, I've mentioned before, for oxygen, it is in its most stable state. Oxygen exists in diatomic particles in gaseous form. So when here O2 gas, diatomic in gaseous state, so most stable state, so the delta H naught formation of oxygen is equal to 0. Or can also be applied in dissolution process of ionic solids. When an ionic compound dissolves in water, there is an enthalpy change. So this is the solid ionic compound dissolves in water to produce Mn+. This N+ is the ionic charge, and this ion must be in aqueous form because we dissolve it in water, plus Xn-, this N- is the ionic charge for X, and it must be in aqueous form as well because you dissolve this Mx in water. So both ions must be in aqueous form. And this is, we can calculate the delta H solution. There are two stages for overall process. The first stage is break down the crystal lattice into isolated gaseous ions. So this solid, we have to break down the crystal lattice in the solid form, break down into the gaseous ion. After it becomes gaseous ions, we hydrate the separate gaseous ions by water molecule. So first, break crystal lattice in the solid compound, make it to become the gaseous ions, and then after that, you hydrate those gaseous ions with water molecules. That's why the final outcome, aqueous state. We can calculate delta H solution from this. This process is called dissolution process. The first stage, breaking the crystal lattice in the solid compound. Here we have sodium chloride compound, sodium chloride solid. This in sodium chloride solid crystal contains Na plus and Cl minus ions. So we separate this Na plus and Cl minus ion, separate them and convert into gaseous state. So this is delta H lattice. Separate, make it into gases. From solid compound, make it into gaseous ion. So that energy required is delta H lattice. This process requires energy. So the enthalpy change of lattice, delta H lattice, must be positive sign, because to separate these ions in solid state to become gaseous ions, this process requires energy. It means it is endothermic reaction. Endothermic reaction to overcome the electrostatic forces between these ions in the solid state. Second stage, after we have the gaseous ion, after we have this ion in gaseous state, we hydrate that ion. The second stage is hydration process. The electrostatic forces between gaseous ions and water molecules, we know that water is polar molecule, so these ions and water molecules cause the ions to be surrounded by water molecules. So this is Cl minus ion. Cl minus ion is negatively charged, and water molecules, in water molecule, the oxygen is delta minus, partially negative, and two hydrogens are partially positive. So the partially positive part will attract with Cl minus negatively charged. So all the hydrogen in the water will be attracted to the negatively charged of Cl minus. These forces is called electrostatic forces. It attracts. Negative and positive attract, so it is electrostatic forces between water molecule and negatively charged ion. For Na+, it is positively charged ion. Positively charged ion will be attracted with negatively charged oxygen. This partially negative oxygen in water. This is water molecule. We have three water molecules here. Each water molecule has one oxygen atom. That one oxygen atom is partially negative, so the negative, partially negative oxygen will be attracted to positively charged sodium ion. This process, the electrostatic force, this process releases energy. This hydration process, the electrostatic forces between the water molecule and the gaseous ion, this process, the hydration process, releases energy. So this process is exothermic reaction. The breaking crystal lattice is endothermic reaction. The hydration process is exothermic reaction. The heat change when 1 mole of solid ionic compound dissolves in solvent or water to form an infinite dilute solution is called enthalpy of solution. So this process itself is called enthalpy of solution. Here, the solid ionic compound becomes ionic aqueous. It is called enthalpy of solution, delta H solution. So delta H solution here equals to positive 4 kilojoule per mole. Delta H solution equals to delta H lattice plus delta H hydration, because this requires 2 stages. First, the solid, you need to break this ion first. Break the ion into gaseous ion. Break, and then it will become gaseous ion. So this is lattice energy. It requires energy to become gaseous ion. This is the first stage. And the second stage, this ion, you react with water, and that is delta hydration. Delta H hydration. So this ion attracts water, and these 2 steps is equal to 1 step delta H solution. So delta H solution is equal to delta H lattice plus delta H hydration. So you apply Hess's law in the solution process. So the lattice energy, this delta H lattice endothermic plus 788 kilojoule, and then plus exothermic of hydration negative 784 kilojoule, and you'll get delta H solution equals to positive 4 kilojoule per mole. Example, use energy cycle method. So here we have to use energy cycle method to calculate the standard enthalpy formation of CS2, given that this is liquid, CS2 in liquid form, given that carbon, graphite, reacts with oxygen gas to produce carbon dioxide gas, given enthalpy formation, and then S reacts with oxygen gas to produce SO2 gas, given the enthalpy of formation, given the enthalpy of reaction, CS2 reacts with oxygen to produce carbon dioxide and 2SO2. So we need to calculate the standard enthalpy formation. You need to write down the standard enthalpy formation of CS2 liquid equation first. This is our target equation. Write down the equation for formation of CS2 liquid. So in order to have carbon and CS2 liquid, you need carbon and S. So you need 1 mole of carbon and 2 mole of S. This is enthalpy of formation. You need to find the value enthalpy formation of CS2. First, write down the target equation. And then you write the equation of the given in the question. So equation given in the question, C reacts with oxygen to produce CO2, S reacts with oxygen to produce SO2, and then CS2 reacts with oxygen to produce CO2 and SO2. Here, the first equation, C reacts with oxygen, and then you write down the value of delta H. And the second equation, S reacts with oxygen to produce 2SO2, and then write down the delta H. Since this is 2 mole SO2 produced, for this one, just for 1 mole, this delta H formation is for 1 mole only. But since your S is 2 mole, so you need 2 SO2 to balance the equation. When this is 2 mole of SO2, you need to times the delta H with 2. So it will be negative 592.2 kilojoule. And then your third equation is CS2 plus oxygen to produce carbon dioxide and SO2. These two are the products. And if you look at here, your CO2, SO2, and your CS2 is the product. You want to make it as the product. So these two must be the reactant. So CO2 plus 2SO2 to become CS2 product and oxygen product. And then if you reverse them, if you reverse this equation, you want to make CS2 as a product, you have to change the sign. This sign must be positive. You have 1 more CS2, so just change the signs to positive sign. It will become delta H3 equals 1072 kilojoule. So from carbon reacts with 2 more S to become CS2, the several steps that you need to take is 1, 2. So just add all delta H1 plus delta H2 plus delta H3. So when you add all, that is the delta H of the reaction. It is 86.3 kilojoule per mole. Example, by using the following equation, calculate the standard enthalpy for the following reaction. So we need to calculate standard enthalpy for 2 mole NO reacts with oxygen to produce N2O4. For this one, this question doesn't state whether you have to use algebraic method or energy cycle method. So it's up to you. I'm going to use algebraic method for this one. First, write the target equation, and then you rearrange the equation given. The equation given here N2O4 as the reactant, and in the target equation N2O4 as the product. So you have to rearrange the equation, and then you will get the delta H for the target equation. This step by step that I've shown you previously, just cancel out if you have the same in the reactant side and in the product side, and when you don't need that in the target equation, just cancel out. Here 2 mole cancel out. You don't need NO2 in your target equation. There's no NO2 in your target equation. Whatever in the reactant must be on the left side, whatever in the product must be on the right side. So for this N2O4 equation, here N2O4 becomes 2NO2. This is the equation given. This must be at the product in the target equation. So you reverse this equation. You have to change this into positive to negative value. So it becomes negative 57.93 kilojoule. And for the next one, 2NO plus O2. So here reactants, 2NO plus O2 are the reactants, and in the target equation they are in reactants as well. So you don't need to reverse this equation, and you don't need to multiply with anything because this is 2 mole, 2 mole, 1 mole, 1 mole. So just write down as it is and write down the delta H. Add these two values of delta H, it will be the delta H for the target equation. So delta H equal to negative 57.93 kilojoule plus negative 113.14 kilojoule, and the answer is negative 171.07 kilojoule.